Hello all. So in this session, I will completely focus on the power on procedure in case of 5G, and we will go very depth to understand that how power on procedure works from very scratch. So let's move on. As you can see this flow, right? The starting point is scan SSB as per 38.213, but prior to that, there are many other steps are there which we need to understand from the scratch. So let's say you have purchased any commercial phone, right? And you insert the SIM of any specific service provider. It could be Airtel, could be Jio, could be BSNL, could be Vodafone as well, right? So what happened exactly in the step 1? And that is called power on and initialization process. So step 1 is power on and initialization process. Power on, okay, and initialization process. Here, what UE exactly do? So UE first starts reading the USIM data. What it does? Reading the USIM data. So USIM data, okay. What it contains? It contains your PLMN list, your PLMN list, okay. Then it contains the security related credential. Second is security related credential. What does it mean by security related credential? It means that it will check the K value, it will check the OPC value and the algorithm which needs to be used. Next is that stored all the cell info. Stored cell info. What does it contains? It contains the last scan frequency. The last scan frequency in case UE has already scanned earlier. And also along with which rat it has scanned. It could be your 5G, could be your 4G, and can be on the different as well, depend on the technology, the rat type which service provider do suppose. Then it also stored the tracking area information. Once these steps done, then next steps come. Step 2 is that initialize radio component for FR1 and FR2 band. So when we talk about the FR1 band, there are the band list, like we talk about N1, we can talk about N3, N78. These are the comes under FR1 band. When we talk about the FR2 band, millimeter wave band could be your 257, 257, 258, 260. These are the FR2 band list. Okay. So these are the first action which UE do. Now comes step number 2. Step number 2. Here UE starts PLMN selection. PLMN selection. No need to be surprised that here I am talking about the PLMN selection before the SSB. Decoding, right? No need to be surprised because UE does this. UE does this PLMN selection even the before the SSB decoding. And I will explain you why and how it is possible. Okay, and this is well explained under the TS 23.122. Okay, so here what is the UE action? What is the UE action? So UE will do first is scan all the RF channel. Scan RF channel. Okay, RF channel to detect available PLMN. Second point, it will use stored info, which we have talked about already. UE action, right? It will use the stored info or perform blind search. So first priority will be that use the stored info and for to detect the PLMN. In case that goes fail, then it will start blind search. It will start blind search across all the band. Okay, and then next comes select a PLMN. select P element. How it will do that? How it will do that? Whether it's a home P element or the roaming P element or the roaming P element, that is completely based on the priority which service provider do that. Based on the priority. Okay. So obviously home P element having the highest priority. So H P element will have the highest priority than your digital P element, B P element, P element, right? So highest priority depend on the service provider. Who said? Service provider do that. Okay. Once this part is done, then next step comes as a cell search and downlink synchronization. Now, before that, going on the cell search and the downlink synchronization, we need to understand a couple of things. Okay, so we need to understand that why P element selection precedes the SIB1 decoding, because we know that once you decode the SIB1, it gets the P element ID. Now question comes, why P element selection precedes the SIB1? To understand that, as per 3GPP, there are many reasons are given. Number one reason is given that conserve the battery. Conserve the battery. Now, how it will conserve the battery? Let's assume that UE has to read the SIB1 on all the frequency, so it will take a huge process, because to decode the SIB1, it has to go through the PSS decoding, SSS decoding, and the PBCH decoding, and it will take huge energy, right? So it will drain the UE battery, right? So that is the reason UE do this based on the stored info to avoid unnecessary SIB1 reading. Second point which is defined is that accelerate camp on procedure. Okay, via how? Via the stored intelligence or stored info. Third reason which is given by the 3GPP is that honor operator policies from the UC. And fourth and final which is given is that maintain regulatory compliance. So let me do that. Fourth one is that maintain regulatory compliance. Okay, so these are the reason which is mentioned by the 3GPP that why initially you do the P element selection before the SIB1 process. But does not mean that in SIB1 it will not do that. It will do that. By decoding SIB1, you will know that P element ID, and then it will match with that earlier one. If it is matches, okay, otherwise it will be discarded. Right? So this is the whole process is there. So step 2 we have discussed, right? Step 2 we have discussed. Now we will move on the downlink synchronization. One more step which we need to understand here is that how you will do the scanning of all the band. Once you select the P element, selects the P element. Now it is know the P element. So what it will do now? The scanning it will do only for the frequency which is belongs to the specific P element, right? So it will start scanning all the carrier which part of the finding P element, and it will do the RSSI calculation of the, let's say they are F1 frequency, they are F2 frequency, and F3 frequency are part of this P element. Okay, so now it will measure the RSSI of F1, RSSI of F2, and RSSI of F3. Now let's say it is neg 110, let's say it is 120, let's say it is 125. This is the hypothetical scenario, right? So whenever a standard says that when the UE measure the RSSI greater than NEC 110, then it will pick those frequency. It will pick those frequency as per the standard, right? So once it picks the frequency, that is done. Okay. Now it starts downlink synchronization process. Okay. One more thing which comes in interview is that in these scanning which we have talked, it is based on the RSSI or based on the RSRP. The answer is very clear. Before the SSB, it goes with RSSI. Post SSB, it comes with RSRP. Okay. Now let's move on the how the synchronization do that. So here we are talking about the SSB frequency. What does it mean? Secondary synchronization block. Synchronization signal block. This is the correct name is synchronization signal block. And it contains three parts. Let's understand what. So SSB, synchronization signal block. It contains three components. Contains PSS, it contains SSS, and it contains your PBCH. Now further PBCH is derived in two parts. PBCH DMRS, and then there is a PBCH data. Okay, so we will discuss in the detail this part, but first what we need to do understand is that SSB. UE need to find the SSB position in the frequency domain and the time domain. This is time domain, this is frequency domain. In frequency domain there is a 20 RB, so out of total 240 20 RB, yes, so it means 240 carrier are there. Okay, and the time domain we have code symbol. Okay, 0, 1, 2 and 3. Okay, so UE must need to identify the position of the SSB right in the ARCR. Okay, now one more thing which you need to understand is that how you will do that. For that, 3GPP has given the solution for that, and that part we will try to understand it. First, let's understand that SSB. Okay, synchronization signal block. Who transmit? G node B transmit it. Who receive it? UE receive it. Now next question. Does G node B always transmit, or there is a periodicity is defined? So answer is there is a periodicity is defined. The default periodicity is 20 millisecond, but this is not the fixed one. We can have the setting of the 5 millisecond. We can go up to 20, 40, 80, 160 and even 320 millisecond we can go up to. But the default setting is 20 millisecond, which is the what 3GPP has recommended, and every vendor follows that. Within this 20 millisecond repetition goes. Okay, so every 20 millisecond G node B is sending the SSB, and now it is UE responsibility to scan this. Okay, it is UE responsibility to scan this. Now next question usually asked in the interview is that does the position of the SSB fixed with respect to the every band? The answer is no, it is not fixed. Let's try to understand it. So position of SSB depend on the two factor. One is that obviously the band which you are going to use, the frequency, and second thing is that SCS, subcarrier spacing. So these are the two factors. Based on that, the position of the SSB in the time domain and the frequency domain will be decided. Okay, that is clear. Now next thing, let's move on the one by one. First, we will discuss about the PSS. Second, we will discuss about SSS. Third, we will cover the PBCH. Okay, let's try to understand that what is PSS. When the UE decode the PSS, what exactly UE get it? Okay, so by decoding the PSS, UE gets couple of information. One is that symbol timing it gets. Second thing it gets is that coarse frequency correction. That is called coarse frequency correction. Coarse frequency correction. And third is that partial PCI identification. Keep in mind this is the partial, not the full PCI identification. So three things: symbol timing, coarse frequency correction, and partial PCI identification. Now let's move on the SSS. SSS. Okay, what you will do once it decode? One is that frame timing, the timing. Okay, and then full PCI, here it able to detect it. And the third thing is that the duplex mode detection. Duplex mode detection. Okay, now let's go on the in-depth part. So when we are talking the PSS, primary synchronization signal, and the secondary synchronization signal, right? Both are having 127 sequence. Both are 127 sequence. Okay, in the frequency domain. Okay, next thing is that how PSS and SSS are generated. The answer is through M sequence. LT was following Z of 2 sequence code, but in NR M sequence is replaced. Now question can be asked, why 3GPP did that? The answer is very simple. In terms of complexity, M sequence is less complex than the Z of 2 sequence code. That is the major reason to introduce here M sequence. Okay, now there are in-depth algorithm are there which we do not need at this point, but what we need to understand is that if someone asks that why M sequence, the answer is the complexity of the algorithm for the M sequence is very easier than Z of 2 sequence code. Right? Now this part we know. Next thing which we need to understand is that when we talk about that after SSS decoding, the full PCI you can calculate. Then how it can calculate? The formula defined is PCI is equal to 3SSS plus PSS. Okay, where PSS is having value 0, 1 and 2. 0, 1 and 2. At the same time, SSS can have value 0, 2, it should be 0, 2, 3, 3, 4. So 3, 9, 9, 9 plus 3. So 1002, right? So 1000, no, it could be 334. 334 should be there. Close to this one it should be. So that maximum PCI can have 1008 in case of NR, while in LT it was 504 was there. So formula is 3 multiply SSS plus PSS, where PSS is having 0, 1, 2 value. Right? Now next thing which we need to understand is that duplex mode detection, which we are taught that duplex mode detection in terms of when the UE decode the SSS is also detects duplex mode detection. So what is the condition? So when we talk about FGD, here PSS and SSS in consecutive OFDM symbol. Consecutive OFDM symbol. Okay, when we talk about the TDD mode, where PSS and SSS separated by one symbol gap. Separated by one symbol gap. One symbol gap. As for example, if I say that gap is detected, what does it mean? Gap detected. What does it mean? It means that U is using TDD mode. TDD mode is there. Okay, so we can easily identify whether FTD mode is used or TDD mode is used based on that, whether gap is detected between PSS and SSS in the time domain. Right? So after that, what we need to understand next thing is that we have talked about coarse frequency correction. This is very, very important. We need to know that. CFC, coarse frequency correction. And that is part of the PSS, which we have earlier understand it. Now, what does it mean? Coarse frequency correction is related with the CFO, carrier frequency offset. When UE or where UE corrects the large CFO, carrier frequency offset between local oscillator and the received G naught B signal. So when UE corrects the large CFO between its local oscillator and the received G naught B signal, that is called the coarse frequency correction. So we need to keep the CFO minimized to ensure that there should be no interference introduced here. Right? Now, next question is that why coarse frequency correction needed? Right? Why coarse frequency correction needed? So before that, we need to understand that source of frequency offset. Carrier frequency offset. So first thing is that if you talk about the source, right? First is oscillator drift. If there is a drift in oscillator, local oscillator I am talking, oscillator drift. Usually UE and G naught B having the oscillator, right? Both UE and G naught B both have their own local oscillator. And the standard drift that is defined is plus minus 10 to 20 ppm. And that is the tolerable length. Is there defined as per the specification. So let's try to understand what does it mean when I say that plus minus 10 to 20 ppm is the tolerable length of the local oscillator. What does it mean? It means that, let's say, if we are using 3.5 gigahertz RFCM, that is close to that is defined for the N78 band. So N78 band, your NR RFCM is 3.5. When I use that, let's say that plus minus 20 ppm we are using. It means that if you multiply 3.5 gigahertz multiply 20, it will become around plus minus 70 kilohertz offset. That offset is frequency offset. Right? So based on that, we can calculate the frequency offset, and if falls under this range, right, this is the tolerable range is defined. Okay, can have the carrier frequency offset can have vary vendor to vendor specific and the test bed to test bed specific as well as. So some of the vendor can have the different tolerable range, but at the same time vendor Y can have some different tolerable range. Right? Is possible. Second point which we need to understand is that the source of frequency offset is that Doppler shift. Doppler shift can also impact your carrier frequency offset. So usually up to plus minus 1 kilohertz in high mobility scenario is defined. So when we talk about high mobility, it means that I'm talking about the 500 kilometer per hour or the metro train, right, which is going 300, 400 kilometer per hour. Okay, especially. So Doppler shift can have also up to plus minus 1 kilohertz in high mobility scenario, and this shift can impact your carrier frequency offset. Third point which can impact the carrier frequency offset is temperature. Temperature effect. Temperature effects. Frequency drifts due to thermal charges. Due to thermal charges. Thermal charges. Right? So these are the source of carrier frequency offset. Right? Now let's see, once we have understand that the source of carrier frequency offset, now we need to understand that the consequences of uncorrelated carrier frequency offset. So those guys who are the working in the lab environment must be aware that carrier frequency offset, in case it comes, then how we basically fix it. Usually we tune with we play with the gain, we play with the TX-RX gain, we basically tweak with the external GPS, we tweak with the external GPS to ensure that the ppm comes under the specified range, right? We can reduce the CFO, because if CFO goes high, this can impact your all other parameters. Your blood will shoot out, your entire the performance of the KPI, right, will be, will be impacted. So we need to understand that, right? So first, let's try to understand that consequences of uncorrelated CFO, right? First thing is that loss of orthogonality, loss of orthogonality, right? Between your OFDM subcarrier. What will happen if orthogonality is lost between the subcarrier? Simply ICI, inter-carrier interference, will shoot off. This will shoot up. Next, your PSS and SSS detection and the PBCS decoding can be failed. So simply, you might have seen in the lab environment that whenever your CFO is high, UE is unable to detect the SIB1. UE is unable to detect the SIB1. Usually you will see that, and that is the 99% chance. If CFO will high, UE will unlikely able to decode the SIB1. So these are the effect if we are not able to bring our CFO, carrier frequency offset, within the specified range. So these are the consequences of there. How we can fix that? We have already discussed. We can fix through by tuning the gain, TX gain, RX gain. You can play with that. You can use the external GPS. Use external GPS to bring back and tune the value, ppm value, and bring back CFO range within the specified range of the vendor which I have given you, right? Otherwise, what will happen? We have already discussed it. ICI will the suit up, right? So if GNODB will send any packet, you will see that UE is failed to decode. If UE is sending the packet, GNODB is unable to decode. The fail, right, to decode it. So the frequency correction is needed. The synchronization of the frequency and the time both should be aligned to proper decoding, right? So these are the consequences are there. Okay, so till now we have discussed PSS, we have discussed SSS. Now next thing which we need to focus is on the PBCH, physical broadcast channel. So when we talk about the PBCH, there are two parts are there here. Okay, PBCH. So what exactly do PBCH having the DMRS and PBCH having the data? Now next question comes in the interview usually that what you do? First it's decode the DMRS or it decode the data. The answer is first is decode the DMRS. Why? Because DMRS gives the quality, channel quality, right? And UE need that. UE need that to understand the channel quality of the channel. then it decode the PBCH data. Once it decode the PBCH data, then it gets the idea about the MIB. Usually most of the people talked about that you decode the PBCH and it gets the idea about the MIB. This is not exactly true at the export level. You should say that when the UE decode the PBCH data, then it gets the idea about the MIB part. Right? MIB part. So finally we can say that my PBCH is the container and MIB is contents of that container. So this is my container, this is contents of that container. Right? Now let's move on. Next question usually comes that what is the size of the MIB? What is the size of the MIB? So that is 24 bit is defined. Okay, 24 bit is defined. Now, once MIB is the what is we can get it? We can get it the through the MIB. We can get it SFN. We can get it core set. We can get cell bar status, the DMRS type A position, right? And the intra frequency reselection parameters. So these are the common parameters. Hope you will be aware about that. These are the basic parameters. Same way, once the MIB is decoded, you having the idea about the SIB1, right? And SIB1 is scheduled via the PDCCH. We already know SIB1 is scheduled via the SIB1. So SIB1 is scheduled via the PDCCH using SIRNTI. It contains what? Again, PLM and ID. These are the very, very important information. As initially I told that to get the PLM and ID, you must decode the SIB1. But now again, you will match this PLM and ID with the earlier PLMN, which it had identified before the SSB decoding. If it is should be matched, if it is matching, okay. It's not matching, simply it will reject. It will reject the PLM. What other parameter? The PLM and ID we have talked. The tracking area code, cell selection parameter, all the parameter QRX level mean, Q quality mean, it will contains, and the scheduling info for other SIB. So all the other SIB, whether it's a SIB 2, 3, 4, 5, and numbers of SIB are there, which is defined by the 3GPP, right? So having the idea from the SIB1 itself. Okay. So this SIB1 contains all other SIB related information. Keep in mind, still we are, excuse me. So these are very, very important, which we need to understand. So these are we are discussed. Till now we have reached here. Till now we have reached here at this point, and still it is going on the process. Still we have not started the uplink. Still it is going on the downlink, right? And after that it will check bar, cell bar, and PLMN is there or not. Based on that, now it will start the uplink synchronization process. Okay, now still the complete process is not completed here. What we need to understand is that still it's not clear how you basically know the position of the SSB, right? So that we need to still understand it. For that, 3GPP has given that option. 3GPP has given the option. Okay. So first, let's talk about the time domain. Time domain. For that, you need to follow the specs. You need to follow the specs 38.213, where 3GPP has mentioned that how you will understand or know. As initially I have told, it depend on the two factor. One is that SCS, and the second thing is channel bandwidth, CBW, or carrier bandwidth, right? Which band it is going to be used. So as per 3GPP, they have classified in three sections. When the frequency is less than 3 gigahertz, then 3 to 6, and then greater than 6 gigahertz. So based on the formula they have defined it. Okay, so let's say there is a one example I am talking about here, but you need to refer the 38.213 to just to give the idea about how the calculation will be. So I am considering one case, let's say A, where I am using the 50 kilohertz. 15 kilohertz is my what? SCS. Okay, and For that, let's say I am using any band which is 3 to 6. Okay, 3 to 6. For that, what 3GPP has defined is that, so it has defined the formula of the starting OFDM symbol. Starting OFDM symbol. How we can know that starting OFDM symbol? That is very, very important. So formula is given that 2 colon 2 comma 8 2 comma 8, okay, and plus 14n. What does it mean? So let's deploy it, and for that 3 to 6 gigahertz, the n value will vary from 0, 1, 2 and 3. So if you put the 0 value, what will be happen? 2 plus 0, that is 2. Next, if you put the 1 value, okay, so next value will be like 8 plus 0, so means 2 8. Now put the 1 value, 2 plus 14 16. Next value 8 plus 14 22. So these are the position of the symbol is possible, right? These are the symbol possible, and we can get it. The starting symbol in this case will be true. Starting of symbol will be 2. So based on that, UE knows the starting OFDM symbol, and it helps is to trace the position of the SSB in the time domain. Same way, frequency domain comes. Again, 3GPP has given the guideline. It's not that any vendor can do, I mean the UE can do any, the on decision, right? No, there is a fixed guideline has been given for that. So now frequency domain, what exactly we are able to, you will do for calculate the SSB frequency is that there is a formula is defined, and that formula is that f point a plus offset to point a, offset to point a plus KSSB. Where you will get the KSSB value? Through the MIB. Once you decode the MIB value, it gets the KSSB value, right? Next thing is that F point A. Okay, prior to that, there is a offset to point A, right? Offset to point A, and then F point A. So these are the information which we needed, right? So how determine the point A? For that, a point A is absolute frequency point A, right? And these provided in the MIB or can SIB could be there. So if you know that, you can calculate the SSB frequency, right? So based on that, you are able to detect the position of the SSB in the frequency domain and the time domain, right? So this is how the overall process triggers from the power on procedure to the how you decode the SSB, right? All the downlink synchronization process, and then it started with the uplink synchronization process that started with the PRAG phase, right? Thank you. That's what the my entire purpose was to explain, so that you can know very in depth that how this entire process goes through that, because most of the people talk very basic that how the downlink synchronization start and the uplink synchronization process start, but very few people goes very, very in depth. Intention of this course is to know as much as in depth as per the specification. Thank you. Bye.